Hey, this is Kyle again, and I'm here to talk about part A2 of exam 3. And that's how we can use the Lewis relation that we discovered in part A1 and apply it to a wet and dry bulb energy balance. So kind of what that is getting at is when you have a wet bulb and you swing it around, water is actually going to evaporate off the bulb. And it's going to, for water to evaporate, it needs to take, it requires heat energy. So that water is going to actually be taking heat from the surrounding air. So that bulb will actually read a lower temperature than the dry bulb when they're both being swung around. So the Lewis relation can come in handy when we're taking a look at the energy balance of a wet and dry bulb system. So first, we want to take a look at the concentration difference of the of the wet bulb and the air around it. So we'll do the mass transfer coefficient, and we're going to multiply it by this concentration of water at the surface minus the concentration of water in the air, or using the infinity sign because it's just far away from the surface. And then, as I said, the water is going to be evaporating. So for water to evaporate, we need a heat of vaporization, or an enthalpy of vaporization. So we need this lambda term. And then we can set that equal to the heat that is being transferred during the process. So that'll be the heat transfer coefficient times the temperature difference. And as I said, the temperature on the surface will be cooler than the temperature of the surrounding air. So we'll do temperature of the surrounding air far away from the surface minus the temperature of the surface. And now we can use the Lewis relation, and with the Lewis relation we can actually get this mass transfer coefficient and this heat transfer coefficient to not appear in our relationship, and that'll make it easier to solve for the relative humidity, which is the end result we want to get to. So first, I want to divide both sides by the mass transfer coefficient, so we'll just take it from this side and we'll divide it to this side. So now if we take a look at this looks pretty familiar, and that's because it's right here as well in our Lewis relation. So we can actually rewrite this equation as the enthalpy of vaporization times the concentration difference, and multiply it times the density times the heat capacity times this temperature difference. So now there's some more simplification we can do that'll help relate it to humidity. You can actually think of concentration and not really simplify, but replace it with terms from the ideal gas equation. So the concentration of water at the surface, well, we know that is equal to the pressure of water, or the partial pressure of water at the surface over the gas constant times the temperature. And then we can do the same thing for the concentration of water in the air. It's the partial pressure of water in the air over RT. So now, just to make it easier, we'll write it as one fraction. And then we can actually replace the density, and density is going to be the total pressure over the gas constant times temperature. So P total over RT. And now you may notice we have two temperatures in this situation, temperature at the surface of the wet bulb and temperature of the air. So maybe wondering what temperature we should use here and here. So it actually doesn't really matter, because with such a small difference in temperature, or a relatively small difference in temperature, once we convert that temperature to Kelvin, which it has to be converted to Kelvin to plug it into the equation, the difference goes, even if it's like 5 degrees Celsius, the difference in Kelvin, 5 Kelvin, is so small mathematically because it would be like 300 and 295 instead of Celsius, where it could be like something like 30 and 25. But like I said, that's such a small difference, but we'll think about it as like the average temperature, just to be safe. And either way, this is going to cancel out from both sides. It's in the denominator. So we have this equation simplified once again. Oh, and I actually forgot to bring down, so we're just replacing the density with this. I still need the heat capacity here. As I said, the gas constant and the temperature will cancel off both sides, so I'll rewrite the equation real quick. And now we can kind of put it in terms of relative humidity, which I'll write over here. So relative humidity is equal to the partial pressure of water over the pressure of water at a specific temperature of water and the saturation pressure. So this bottom part we can actually solve for with an Antoine equation. So we know how to get that value, and then the partial pressure of the water. Now that we have all known elements in this equation, and we don't have to worry about the heat transfer coefficient and the mass transfer coefficient, we can actually isolate the partial pressure of the water, and we can we can kind of put it in the relative humidity equation, and we can actually know the relative humidity, and we wouldn't be able to have done this without knowing this Lewis relation. So that's kind of one way we can show how important the Lewis relation is in chemical engineering.